much. Okay, first, thank you everyone for, this is the last talk, so thank you everyone for organizing this conference and for coming and all of those things, and maybe I'll say that again at the end so people can applaud for the organizers. But first, I'm going to start with not this talk, because, I mean, I'm a little bit peripheral to this community, but I realized as I was here that one of the other things I do is some stuff with solving Dyson-Schwinger equations using tubings, and I think there's a number of people here who also care about tubings for other reasons. So I'm going to start by talking a little bit about tubings. Hopefully nobody minds that too much, and then I'll talk about that paper with Bruno, which is what I was asked to talk about, which is about relating phi p tree amplitudes to the sort of story that you guys have been talking about all week. Okay, first just a comment. So the other thing I'm going to talk about is in fact tree level, but I was particularly excited to come here and see that there was so much enthusiasm about the loop level story, because to me a lot of the really cool stuff happens there, and this is also a loop level story. So what do I want to say? Well, so what am I going to get? I'm going to get combinatorially nice series solutions to Dyson-Schwinger equations by tubings of rooted trees. And if we, what kind of tubings am I talking about? Well, they're one of the kinds that shows up before. So what kind of tubings? These are the ones that Thomas was talking about, the maximal B tubings. Which we call binary tubings. And now, what am I tubing though? What I'm tubing is actually slightly different. I'm not tubing the Feynman diagram itself. I said tubing's a rooted tree, so where the heck are the rooted trees coming into? So what am I tubing? So it's not the Feynman diagram directly. But an insertion tree. So you want to make a tree of the subdivergences and how they sit inside each other, and then you say, wait a second, what if there's overlapping subdivergences? And if there's overlapping subdivergences, I want you to think about the sum of all the different trees that could lead to that divergence pattern. Okay? So those are going to be my trees. They're insertion trees for the Feynman diagrams rather than the trees themselves. And so they're naturally rooted trees. The root is the outermost primitive diagram, the subdivergent-free diagram, into which the other things are inserted. Okay? And so, since these are rooted trees, you can see there's another way to see what kind of tubings they are. They're also the special case of Pasha's poset tubings, where you think of the rooted tree as a poset. I know he didn't talk about those here, but there's something that certainly me and my collaborators have been pretty excited about. So, okay, how about an example so that we know what the heck I'm talking about? I'm aiming to keep this on just this side of the room, but we'll see if that happens. So here's a rooted tree. Now what am I going to do? I'm always going to have an outermost tube that's going to cover the whole thing. And then every tube I want to break it into exactly 2 subtubes, and a tube in this case is just a connected subgraph, tree. So there's one way to do it. Every tube of size at least 2 I'm going to break into subtrees. Obviously, if it has size 1, I can't do that. Okay, so let's see. I'll do this. All right, make sense? Okay.
Sorry, do you have to always break it up into 2, or can you break it up into like 3?
I always want to break it up into 2. That's corresponding to the maximal case here. So if you don't break it all the way up into 2, well, I mean that happens too. And if you want to make a associahedron kind of thing out of it, you're going to want those ones as well. But I only need these ones where you always break it up into exactly 2 for solving my Dyson-Schwinger equation.
Okay, thanks.
And there's another way you can see this, another way you can see conceptually where it came from. It actually comes from iterating a linearized version of the Konkheimer coproduct. And in one of the talks earlier, there was that sort of triangle relating the physics, the combinatorics, and the geometry. And I have to say, personally, I'm not much of a geometer, so I don't have a ton of geometry in here. I mean, there can be some. Again, there's a perfectly nice associahedron in there, relative of a graph associahedron. But there is an underlying algebraic structure that I think is playing a sort of similar role, in the sense that I'm not going to tell you about the proofs because I want to get onto the other thing I'm supposed to tell you about. But if you have heard me years ago talk about a rooted chord diagram approach to similarly solving Dyson-Schwinger equations, where the proofs were hideous, grinding recurrences, these proofs are conceptual because of the algebraic structure. So in a similar way, the third side of my triangle is algebra. Yes?
Do you assign some functions to the student?
Absolutely. Well, functions might be a stretch, but some monomials anyway.
Okay.
So I need to tell you what my setup is. So this is sort of the physical side of the setup. I'm not going to write down the general case. Let me just give you a simple example, and this is now a very old simple example. And this is in a piece of Maslow's-Yukawa theory. So I'm going to call my Green's function. I use very weird mathematician notation, I apologize, which I started doing years ago, and I don't think it's going to change. So something like this. So here's an example of the kind of thing I mean by a Dyson-Schwinger equation in notation that's just a few variable changes away from what a physicist might recognize. So what's going on here? I've got some Green's function. In this case, it's just some graphs like this in a Maslow's-Yukawa theory, but not even all of them, just the ones that are made out of iterating, putting that single one bubble into itself. So this is a very simple example. What am I doing? So here's the integral for the bubble itself. Here's the recursive insertion of that's giving you the recursive insertion. It's in the denominator because it's an inverse propagator, because I'm putting in a geometric series of these if you want to think about it mathematically. So in terms of tree counting, this is sort of just a generating function story where you say, if I take the trees that come from 1 over my trees, the subtrees are 1 over the trees I started with, that's a list of subtrees. So by standard generating functionality, you're getting plane rooted trees. I'm going to renormalize by subtracting at a fixed reference scale. Because this is recursive, this will automatically do the renormalization correctly, so I only need the outermost subtraction. So that's the kind of Dyson-Schwinger equation that I'm talking about. My L is my log of my overall scale. Okay? Now, the things I'm going to tell you hold in a lot more generality than this. So what I'll do works also for, we can certainly do systems are okay. We can do Here there's just one, you can call it one kernel or one primitive or one skeleton. I don't really care what you call it, but there's only one, and it's in one loop. But I can have as many as you like at any number of loops. Primitives at all loops. Any loops. I can also distinguish insertion places. Here there's only one insertion place. I really should put the arrows on there. I'm always inserting along that line. So more insertion places. In fact, I think we've pretty much got everything that's going to come up physically except, there's one big except, the things I'm going to do are very intrinsically single scale. So you'll notice there's single scale. So but single scale. I said that briefly because that was really meant for the physicists to have some idea what we're talking about physically. I hope it was helpful for that. If you're more of a mathematician and you have no idea what this half of this board is, don't worry about it because I'm about to actually tell you how to solve these things, and they're more general versions. Right? Good? Questions? Okay, so what do I want to do? So, of course, you know, you still need to actually like do some kind of integral somewhere, right? So the only thing I'm going to need is the regularized versions of the integral of the primitive diagram. So in this case, we're going to call this f of rho. F of rho is going to be just the regularized integral of the primitive. So I'm going to choose some unit vector here, so k squared. But now this is going to go to a 1 plus rho, so we're doing an analytic regularization at the insertion place. If there's more than one insertion place, there'll be more than one row, and this will be multivariate. That's perfectly fine. So you have that guy, some regularized integral, and then in general, I always want to write this as a series expansion. It should always have a simple pole, so have some log divergent kernel. So I'm going to write this as fi rho to the I minus 1, I greater than 0. And that's, like, this is for the specific example. This is what I want my setup to look like in general, except, of course, there could be more variables. There can be different f's for different primitives. There can be different f's for different primitives in many different ways from the system, from the different primitives at different loop orders for a given equation. And there can be multiple rows for different insertion places. Okay, and so now, what's the solution? Okay, I'm going to fail to get it on two boards because I want to show you the differential equation. That's what I wanted to show you most. So what is the solution? Because I didn't actually write out exactly what the equation is in general, I'm not going to write out exactly what the solution is formally, but I want to give you an indication of how it's done. So first, you need to solve the purely combinatorial tree equation. And so I'd already said in this case the tree equation is the equation for plane-rooted trees. And so that, in this case, so in the example, that's t of x is x plus 1 minus 2x. Right? So if you know your generating functionology, this would be like a sequence operator. So, and b plus is at a root. A root, which you don't normally have notation for in a usual simple tree class, but you could. So this is a kind of thing that I haven't got into enough detail for you, but it's really just sort of classic generating functionality. You can always solve for these simple tree classes. The ones that are going to come up in physics are almost always just going to be something related to either k-ary trees for some k or plane-rooted trees. And so those are all solvable just with some following factorials and simple things. Okay, and then for each tree, you take each tubing in the sense that I have, and then each tubing has a contribution. So then sum over trees, tubings of the trees. Each tubing contributes. Okay, and here I'm going to cheat slightly to keep it simpler. So what is it going to contribute? So you're going to take a product over the vertices in the tree. And now what you're going to do is each vertex in the tree is going to contribute one of the f's from this. So what is the f? It's something we're going to call the rank of the tubing at that. So each tubing tau contributes something like this, the rank of the tubing at that vertex. And now, here's where I'm going to lie slightly. This is just what it contributes to the anomalous dimension, which is the coefficient of L in here. And you can do the rest of the Green's function, but I'm not going to tell you what that is for today. It contributes this to the anomalous dimension, which is the coefficient of L in G of XL. Okay, there I'm using your usual enumeration notation for coefficient extraction, where I put the coefficient in square brackets before the thing, and that's as I want the coefficient of that guy. Okay? So, I didn't tell you what the rank is, and I'm going to tell you on the example. So when you were saying, do I have a function on the tubings? That's what I'm going to calculate on the tubings. All right, and what is the rank? I'm going to change color for the rank. The rank is 1 less than the number of tubes rooted at that vertex. All right, so here, look, there's 1, 2, 3 tubes that are rooted at this vertex. So the rank here is 2. Here there's just 1 tube rooted at this vertex, so the rank is 0. Here there's 1, 2, 3, 4 tubes rooted at this vertex, so the rank is 3. And these leaves, well, leaves kind of always have to have rank 0. So the product in this case, you're going to get an F0 to the 1, 2, 3, 4. Then you're going to get an F2 and an F3. Is the contribution of that tree. So that's the sense that I have a function. And then that really does it. That gives you a really controlled series expansion for the Dyson-Schwinger equation. And now you might say, wait a second, I already had a series expansion because I had the Feynman diagram. But each Feynman diagram contributes something really quite complicated, right? Whereas now we've taken all the complications, we've just put them, the only place that the analytic complications come up now is in the series expansion of the regularized primitive, and now we know exactly how those go together just by looking at these tubings. And they tell us exactly how to put together the coefficients from those series expansions into the actual Green's function for whatever process your Dyson-Schwinger equation is for. Okay, but what I wanted to get to was the differential equations. So, well, this story, I should say who these stories are with. So this first part of the story is with a number of my students and collaborators, Paul Baldouf, Amelia Cantwell, with Kurush Ibrahim Ifard, Lucas Nagergal, Nichols and Harris, and myself. And it was one of these things where we were all sort of doing some slightly different things, and then they all came together and ended up being the same thing, and that was really nice. And then the version with the more insertion places is with my student Nick, my finished student Nick. But I want to tell you about how you can use this to get some really nice sort of pure generating functionology kind of differential equations. I guess I'll put that over here. I was trying to keep it on one side, but it didn't quite happen. So also, and this is work with Gerald Dunn and Mishi Borinsky, here's an even more special case. Well, it's not even more special than the one, how about just say a special? Good enough, a special case. Because what's going to happen in the special case, if f of rho can be written like this, then, and so I'm just going to show you an example, because again, I want to get on to what I was actually supposed to talk about. Okay, and if you say, why that example specifically, that's actually the example if you want to do the phi cube propagator. You're going to get this example coming out in the end. Then you can do an extra layer of combinatorics where you have an alphabet, you actually have K alphabets, and you have words on those alphabets with certain constraints, and you put those letters on the tubes. And from that, again, using pure generating functionology that I could get my students in enumeration to do as an exercise, you'll get a differential equation for the anomalous dimension. So you get this differential equation for the anomalous dimension. Sorry, so I'm going to break it into 3 pieces based on what alphabet the letter for the outermost tube is from. So I guess it's actually a system. It looks like this. So this is this plus sort of that original shape, but with a possibly different go there. Anyway, L2. You can probably guess what the last one is going to be. 6 gamma of x, 2x, e to the x minus 1, x plus L1 plus L2 plus L3. Okay, so the point is that's an extremely structured system of differential equations that I can basically just read right off these. Like, it's not a coincidence that this goes 2, 3, 6 and this also goes 2, 3, 6, right? Those are the same 2, 3, 6. And every piece here is pure combinatorics. This is about saying what tree you're inserting into when you make. If you make one of these, you can imagine this as this subtree inserted into this subtree. And that's exactly what this is saying combinatorially. Because this is the differential operator is pulling out the number of insertion places. And so this is the tree you're inserting into with a marked insertion place. And this is the tree that you insert into it with a multiplicity for the number of ways to label the new outermost tube. So this is every single factor in this it's completely clear combinatorially what it's doing. It means you can very easily read off special cases. Suppose you want to do just rainbows or you want to do renormal chains or something like that. You can just, you say, oh, well, clearly I've changed the number of insertion places, so I changed the differential operator. I've changed what I insert, so I changed this factor. I've changed what I insert into. You can immediately create all of these things and you know exactly what every term is doing. And it's exactly the right shape for doing resurgent analysis. So if you wonder why that's a paper with Gerald Dunn and Mr. Berensky, the answer is this was just the right form for them for doing their resurgent analysis. So you want to try to understand, you want to try to understand the instanton expansion or things like that. You're in the right place to do it with this purely combinatorial differential equation. So that is what I wanted to say about differential equations of tubings of rooted trees. Because other people had tubings of trees and differential equations. And this is quite a different place where they show up, but again, a place that I hope you can see is physically interesting. Okay, comments on that before I actually talk about what I was supposed to talk about today? Well, hopefully at least somebody appreciated it. So that was not this talk, so now this is this talk. Okay. So now we are going to go back to tree level. This is a tree level story. And the way it came about, incidentally, is I was external examiner on his thesis, and he had a conjecture in his thesis. And I was like, I can prove that conjecture. And then we wrote a paper. So that's how this came about. So what is this story about? So we already heard from Nick about the global Schwinger formula. And so that's where this story begins, right? So Nick and Freddie had this global Schwinger formula. Okay, and I'm just going to write it down. Just we have here something like this. Where we have this Fn, which is some like this. So I actually don't remember exactly what form it got written up earlier in the week, but it's going to look something like this. And then this is in the tropical, so this is in some positive tropical Tasmanian world. And I guess I should tell you how I'm parameterizing so that you know what these variables are, and that'll also explain why they have an annoying shift. So how do I want to parameterize? So, I mean, it's pretty much the standard one. I'm going to do it this way. But here I want to put sums, right? So 1 plus, say, an x1 tilde, 1 plus x1 tilde plus x2 tilde. It's this parameterization, right? And then the xi's are the tropical. Xi's are the tropical position. Okay? So that's all fine and good, and people studied this, and it got mentioned earlier this week, and I sort of hope that you guys are vaguely familiar with it. But suppose you want to do, and this is something that I think Freddie had been thinking about for a little while, and I understand that Bruno was not actually technically his student, but he got really excited in one of Freddie's problems, and so he started working on it. I think that's the correct history of what happened here. So what happens if you want to do this story, but you want to look at the phi 4 amplitudes or phi p amplitudes? We're going to do phi 4 first, and then we'll move on. So what about, and in particular, I think part of what was exciting here is try to relate them together rather than just sort of redoing it. And so one thing you could do is you could just have a similar global Schwinger formula, but you just want to localize it to the region where you have only the 4 valent vertices. Okay? And so you could do that just by writing an equation where that happens for that region. So one thing you can do, you can localize to some place where where there's only 4 valent vertices. Okay, and here's what you end up being. So this is the region. So you want the region h of x equals 0. And what is h of x? This I have to copy down so I don't get it wrong the first time. I mean, I think you just work it out and it's what it has to be, but I'm not going to work it out live on the board. That would be a mistake. Okay, so you got that. And now, let's see, where am I going to go? I guess we're done with not this talk. So. So, what Bruno conjectured in his thesis that these guys, this is indexed by some non-crossing chord diagrams. So, in the following way. So here's how it works. For a chord, so he uses this theta notation for chords, so that's the chord from the point A to the point B. And if you have a chord there, then that means those two are equal. So you set x, except there's a shift in the indexing, so it ends up being xa minus 3 is xb minus 3. This is one of those things, and in retrospect, perhaps, the indexing should have been different from the beginning, but it was not, and then you're stuck with the mistake you made. I made a stupid sign choice back in my thesis that I still suffer from. You know, gotta watch out for that. And if one chord surrounds another one, is outside another one, so, or nest, one is nested in the other one, but AB is going to be the outside one, so surrounds. CD. Then you have a strict inequality. Maybe I don't want to say that. Maybe I want to say that. So xa minus 3, we already know that's equal to xb minus 3, and those are strictly less than the inside ones. Okay, so if you have nested chords, then the values get bigger as you go inside. Okay? It's a thing you could do. Why not? I don't know if you find this surprising or obvious, but you know, it's not too bad to prove once you sit down to do it. Maybe I will just do a quick example so that you see why this is not actually mysterious, and I will not actually show you the details of the proof, but let's do an example. Do an example. So what do we have in this case? There's two chord diagrams. They're going to be labeled, because of that annoying shift, they're going to be labeled like this. And there's only two non-crossing chord diagrams on 4 vertices, and those are the two non-crossing chord diagrams. And now, so how does this end up working out? So let's just write out explicitly what the h of x is in this case. So what are my variables? I have an x0, an x1, an x2, and an x3, and that's all that I have. And then I'm going to have minus 2 times the minimum of the consecutive pairs. So I have x0, x1, x1, x2, and minus 4. Okay, I guess it's not there. And then I've got the 3. Whatever, like that. So now, the first thing you want to notice, let's think about what's going to happen with, say, the x0 in here. Right? So the x0 clearly attributes from this term. Now in here, it might or might not contribute, depending on whether it's larger or smaller than the x1, but it at least potentially could contribute. But there's a 2. Okay, there's no x0 in there. There's an x0 here, and there's a 2. So the first thing you want to notice is if this is ever going to be 0, it's going to have to be the case that x0 is equal to one of the other ones. Because otherwise, by parity, I'm never going to be able to get the x0s to all cancel out. Right? So by parity, x0 must equal xi for some I greater than 0. Okay, well now let's think about what that could mean, right? So what if x0 equals x1? Well, if x0 equals x1, then, sorry, it's here. Looking here, we see, okay, that means that's this chord. Right? That's the x0 equals x1 chord. And then you have to go back, and you've gotten rid of those, and you have to go back and look at the x2, and then you make the same sort of argument. The x2 has to equal something. If they're all equal to each other, well, that's actually the union of these, that lives in here, side here too. But then x2 has to equal x3, and that gives you this picture. All right? On the other hand, if you'd made x0 equal to x3, you'd find this picture. And if you make x0 equal to x2, then you'll be forced to make them all equal. So that's the special case of this picture where they happen to both be equal. Okay? And that's, how does the general argument work? The general argument is actually not that different. It's just a little bit more of a pain to do the counting. What ends up mattering is around a given x. So first of all, imagine putting, I think it's easiest to think of a pre-order. So it's like a total order, but some things could be equal. Put that structure on the x's, and now around any given xi, what you care about is how many of the indices before and after are less than, or no, I guess are greater than it. So it would be the minimum in that region. And those two indices, the parity of those two indices basically determines everything. So you play a counting game, and then you get it. It's kind of fun. I like counting games, so. Okay, well, what about 5B? So it should be basically the same story, but now your chords, instead of having 2 ends, they have to have more ends, which is maybe what you would expect. So, for instance, you might get something like that. Is that the example I wanted to do? 1, 2, 3, 4. No, I want the example 1, 2, 3, 4. Yeah, that's the example I wanted. So you get things like that. Now, it's not a mathematical theorem that's actually going to work the same way, but it will. Well, the real problem is that Bruno and I are both doing the things, so it didn't get done. But I am quite confident that the same situation is going, the same story is going to work. He's computed it in a lot of concrete examples. The combinatorics is not actually the hard part. Some of the translation to get to this style of formula still needs to be done. But I don't think there's any fundamental obstruction. You just haven't done it. Yeah, so similar story with these sort of, and that's a kind of generalization of chord diagrams that you see in other places, right? The chords just now have more ends. Okay? So, yes. So this guy, this would be, you have 4 was giving these 2 ends, this would be 5, 6, it's always 2 more ends than the chords have. Okay. There's just a couple of things I still want to say about this, and I have some minutes, so it's perfect. Because there's a couple questions you might ask. Like, how do you get your trees back? Right? Where are our trees? Our trees are gone. So,
by the way, wouldn't you call that object non-crossing partition?
yeah, it's totally a non-crossing partition. But it's a non-crossing partition where all the blocks have the same size. So that's the story. It's a story of non-crossing partitions with fixed block size. Okay, so how do we get our trees back? And this probably won't surprise you. At some level, the first thing you're probably thinking when you're thinking, how do I get my trees back, would be some sort of triangulation story. Right? Now, in this case, the triangulation has to be a quadrangulation, but it's basically what you might guess, something like a triangulation. And so I'm going to show you in an example. Let's do let's do n equals 8. So what are the chord diagrams in n equals 8, the non-crossing chord diagrams? So it goes 3, 4, 5, 6, 7, 8 is how the indexing goes because of our annoying indexing. So what is there? There's that one. There's that one. There's that one. You guys know how many there are, right? It's Catalan. So you know when I'm going to stop. I'm going to have to stop when I get to 5, and I clearly didn't leave enough space, so that was sort of silly on my part. Because there's still one more. So I guess maybe I'll just say n equals 8 up here, and then we'll put the last one here. Right? This is Catalan, so I had to get 5 of them, and now I got 5 of them. All right? So now what am I going to do? Well, the first thing I'm going to do is add an extra chord on the outside. At some level, you can think of this as fixing the indexing. It's going from 2 to 1. Oh, sorry. And now let's look at, notice there's these regions, and they can have, actually I don't want to worry about that little one. Let's worry about these regions. These ones are sort of internal. I want to worry about how big they are. So these ones are all the smallest they can be. If you put the line here, then they really are all squares, right? So those are fine. I can't do anything about those. But now these bigger ones, I need to split until they also are just squares. All right, so what color? I guess I will use the red for this. let's do this one first. So I want to put a new chord. I think that's the right parity. There's a parity condition, and I haven't done this in a while, so I've forgotten. Yes, that's the correct one. This is very much a story of parity conditions. Okay, and then what's the other one? The other one is this one. Okay, and you can start to think about what the parity condition is. And we'll have the same sort of story here. So we have that one, or we have that one. For this guy, this one, this one. And now for this guy, there's nothing. This guy just doesn't need any of these, but this one needs two of them always. So I have more possibilities. It looks like this. Okay, what can I do? It's sort of likewise, well, I'm going to let you guess the parity conditions. Oop, nope, that's not right. You won't be able to guess the parity conditions if I do it wrong. Good job, me. Okay, this one is supposed to go all the way over here, and then that means this one goes like that. There, that makes some more sense. That actually works. Okay, and then I have this one. No, it's still wrong. Oh, you will never guess the parity conditions if I draw it wrong. Okay, now that one is correct. It was just sort of skewed on my page, and so it didn't come out right. Okay, here we go. You're almost done. So if you were sitting there trying to figure out what the parity conditions were, you will probably quickly notice that if you ignore this outermost one, it's pretty clear. I'm going to always start here on the right of something, and I would always end here on the left. But then the outermost chord is backwards. But of course that makes sense, because if I actually put them on a circle instead of a line, the outermost chord is kind of going the other way. And so that's the correct parity condition. Okay? And now, just take the dual trees here, and they'll give you your trees back. So I'm not going to do all of them, I'll just do one, because I think you guys know about dual trees pretty well. So, and this would be 3, 4, 5, 6, 7, 8. This was the 2, this was the 1, another indication. And so, what's going to go on with this dual tree here? Well, oh, that's not the one I had on my page. I had a different one. Did I draw one of them twice? Oh, sheesh. Sheesh, that's not the one I wanted. I wanted this one. That's the one that's missing, right? Because I had that one twice. Now I actually have a different one. Good, yay, different one. Okay, so, and how am I going to have my dual tree? So there's what is going to happen with the vertex here. I'm going to label, the labels are going to shift just this way, slightly. Okay, so in here I'm going to have this vertex will be 7, this vertex will be 8. So I've got some 7 and an 8. And then what's going to happen after that? That guy is going to have to connect here, and this guy is going to have to connect here. So I'm going to set here's to the 7 area, the 8 area. Going on here. What else is going to happen here? Well, this guy is going to have the 1, and then the 2, and then the 3. And then in here, off the other side, what am I going to get? I'm going to get the 4, the 5, and the 6. As you would expect. All right. So that's nice, and you'll get basically the same story here with your other set partitions. And then the last thing that I think was interesting, I hope this this community will find interesting. They're giving you any indication of how any of the proofs work, just what I think were the highlights in my mind of the paper. And this is the other one that unfortunately there are some details that remain, and that since I think neither of us are working on this, may not actually get completed, because there's a connection back to, I think, a story many of you will be more familiar with, which are these doubly ordered cubic phi cubed amplitudes. So oh, I would just point out, just as a minor comment, this does induce a nice partition of the set of the trees here, because there's the ones that came from different chord diagrams. I don't think that's enormously exciting, but it's sort of nice. So how to connect back, or connect, maybe back is not the right word, to these doubly ordered amplitudes. So what are these doubly ordered things? I kind of am guessing most of you guys have seen these things before, but the point is now, in the same way that you have trees, right, so you have trees with the leaves, with a cyclic order on the leaves, and then labels. And so here the labels went 1, 2, 3, 4, 5, 6, 7, 8. For a doubly ordered amplitude, doubly ordered, they want to be consistent with two different orders. Okay, so the tree doesn't come with its planar embedding, but it's a tree for which there is an embedding that's consistent with the one order, and there is an embedding which is consistent with the other order. Those are actually kind of fun objects. Okay, so this is trees compatible with two cyclic orders. And one of the, so this is something that I think that Freddie Cacciazzo had studied a fair bit, and in particular with some collaborators, one of the ways they looked at this was with what they were calling polygon decompositions. So one approach to these, which by some people, was these polygon decompositions. And the idea is you put one of the cyclic orders actually on, without loss of generality, one of them is the identity, so let's draw it on a circle. And then I actually just draw the other one, going around the circle in some way, right? So if this guy goes from here to here, and then over here, what can I do? Something like that. And then that gives me some regions. Okay, and so they do some stuff with that. So you look at those regions and you get to read off what the amplitude is. And we can likewise get this kind of region from these sort of regions, right? The things that I was triangulating, or quadrangulating, or however you want to say it. And Bruno called those meadows. So let's call this a meadow. And so what he observed in his thesis is that you can say what size the polygons are going to have to be just from the meadows, and it's the same sort of thing. It's just a shift of the size. Okay, but now I'd like to do a little bit better than just the shift of the size. We'd like to be able to say something about what the indexing ought to be. Right? So let's do an example. So I picked a slightly bigger example this time, because I think it will illustrate better what's going on. So here we go. And what are these meadows? They're just these regions. So there's this one. And then there's this one. Those are going to be my two polygons. And how do I do it? Well, let's do it recursively. Let's start on the outside. And this guy, that's going to be sort of my root. So I'm going to put my root here. And then I'm going to take this meadow, but I'm going to contract up this guy. And I'm going to contract up this guy. So what do I have? I've got a square left. This vertex of the square is both 3 and 4. And this vertex of the square is both 5 and 12. Okay? And now let's recursively do that again if there was another meadow inside. So we'll do that here. Now this is the root of this meadow. And then this gets contracted up, this gets contracted up, and this gets contracted up. Okay, so I want to hang off here. This is going to be my 5, 12, so I'll take the 5 away from here and just leave the 12 here. And then what do I have? I have an edge to the 6, 7. I have an edge to the 8, 9. I have an edge to the 9. Not the 9, I already have a 9. 10, 11, and then back to the 4. And so you're like, okay, great, that's polygons. And in fact, it tells you something because you get the amplitude, or the contribution maybe of this guy to the amplitude as a product. There's a factor for these vertices, and then there's a factor for each meadow as a product of these doubly ordered amplitudes. Or maybe, yeah, okay. Okay, so that's kind of nice, but there's something really hairy about the indices that we don't quite understand. And so I have one, it's actually going to be perfect timing, but there's an indexing subtlety. And one of the first guys where you see that indexing subtlety is actually this one. So you try to play that game with that guy. So I still need to add this, or you could add a part, a larger part. I don't really care. It actually conceptually to me makes more sense to add this part, but I don't really care because that's not going to end up mattering. And then you try to play that game. So actually, I'll keep it simpler for the moment. I'll just put this as the outer guy. Keep it simple. What's the indexing? Well, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 1. And you try to play the game, and you get a nice triangle, and you get another triangle. They're all triangles. And this is a square region here, so it'll be a triangle when you play this game. Similarly for this one, similarly for this one. So it's 3 triangles. They're going to have to be joined like that because that's the structure here, right? This one through this goes to that. This one through that goes to that. And it starts out okay with the indexing. So this ends up being 3, 4, 5. Sorry, no, this one's just 3. Because that's 3 is by itself. This one has to be 4, 5, 6, 7. And then you're like, okay, we're doing okay. The 9 ended up being here. And this gets up being the 10, 11, 12, 13. And this ends up being the 14. But the 8 can't really go here. So Bruno put the 8 here, which, well, okay. Anyway, the point is it doesn't quite work. There's a subtlety with trying to make the indexing do everything you want it to do. And okay, you can set up a rule, but it's a little bit ad hoc. It's not completely clear what the general rule should be. So I guess I'd say that's work in progress, except I don't think we're working on it, so it's just work. And I think I'm almost perfectly on time, so that was, I guess, an overview of something I think is cool that I hope some of you guys thought was cool about tubings, which is where we can do these expansions of Dyson-Schwinger equations, which is a different place where combinatorics and quantum field theory come together, and something I think is exciting because of the high loop level and because of the generality to which it applies and its ability to connect to resurgence or instanton analysis of these series. And then this story about the chord diagrams and the connections back to the trees and the doubly ordered amplitudes that Bruno and I looked at as a sort of project that came out of his thesis. So thank you very much.
So, are there questions for Karen?
I think related
get to the indexing at the end, in the like in the case of the square and the pentagon, how do you distinguish between the 5 and the 12? Like which one stays attached to the square and which one moves down?
So it ends up being you want to take, you always want to sort of tilt it this way, because this was the special edge, the root edge, and the root edge should always have its left side hanging down and its right side going up. At some level that's a convention, but that's the convention that seemed to work most neatly with other things.
Other questions?
How does, it's a similar type of question, but because we're on a cycle, so the 1 is somehow like to the left of the 2? Should I be thinking of it that way, or when you're doing this
Yeah, you should think of it on a
composition?
cycle, yes.
Okay,
Yeah.
but in that case, the 1 isn't to the left of the 2 on the square, so it somehow is broken.
Oh.
Like there's some
Yeah, the thing is, yeah, you're right, because there's two ways to think about it. When you're doing this construction, you have to root each region, and there I have to make a choice. So there I do break the cycle. So you're right. For the point of view of the indexing, you've chosen a root, so you've broken the cyclic structure, and that's why the 1 is on the sort of wrong side.
Further questions? Okay, let's try Karen again.
And since this was the last talk of the conference, I think we should thank all of the speakers for the whole conference. So let's thank everyone. And we should also thank the organizers of the conference.
And especially Svika, who did the bulk of the organization work. So.
Do the organizers want to add anything?
Yeah, I want to also thank everybody for coming and for the speakers for wonderful talks, and I hope you had a fruitful and enjoyable conference, and thank you very much.
Maybe the last people we should thank is our venue hosts, who I think have done a really good job.
Yeah.
At least from what I've seen, I don't know what the organizers have seen, but from my perspective as an attendee, I think they've done a great job and we should thank them.
Yes.